Thank you, Oded, for the introduction. My name is Yael, and today I'll be presenting my PhD thesis on the formation history of lithospheric and sub-lithospheric diamonds from the Voorspoed mine in South Africa, advised by Yaakov Weiss and Oded Navon here at the Institute of Earth Sciences. So why diamonds? That's usually the first question people ask me when they hear about my research. And since people are curious beings and we tend to explore our surroundings, we've achieved great distances traveling outside the Earth. Humankind has reached a distance of over 400,000 kilometers into space, not to mention spacecrafts which have traveled much further than that. But into the deeper parts of the Earth, we've only been able to drill, a depth of 12 kilometers, leaving us to look for more ideas and ways to explore the deeper parts of the Earth. For that, we look at diamonds. Diamonds originate in the lithospheric and sub-lithospheric roots of old cratons between 120 and 800 kilometers, and they serve as windows into the deeper parts of the Earth's mantle. When diamonds form, they capture parts of their surroundings and they encapsulate them inside the diamond. They preserve them for millions of years, and during their ascent to the surface of the Earth, with large magmatic eruptions that are called kimberlites and lamperites, and they give us the opportunity to explore the interior parts of the Earth that have not been changed. So the lithosphere is a pretty wild place. It's experienced depletion and melt removal episodes and metasomatic enrichment events involving carbon and water-rich fluids. These events reflect major tectonic events, and during these events, diamonds form, and they record them, giving us the opportunity to explore them and see the different processes in the deeper parts of the Earth's mantle. So the more commonly known diamonds, the ones that we use as jewelry, and sometimes people pay thousands of dollars and use them as engagement rings mostly, are called monocrystalline gem-quality diamonds. These diamonds have a clear appearance, and sometimes they also capture mineral inclusions. Here you can see a monocrystalline diamond with a garnet inclusions in the center. These inclusions provide a snapshot of the surroundings where these diamonds formed, and they give us different information on the temperature, the pressure, the host rock, the formation lithology, and the age of this diamond. Luckily for us, we also have what's considered ugly diamonds. They're not worth a lot of money, but they're much more valuable for researchers, for geologists, since they're called fibrous diamonds and they reflect fast growth from a carbon supersaturated media. And during their growth, they trap many sub-micrometer inclusions. So this opaque look that we can see at this diamond, if we zoom in, we can see it's actually composed of these million little dots, and these little dots are micrometer inclusions. So the past 35 years, Oded Navon and Yaakov Weiss's group have been studying these micro-inclusions, revealing they have a composition of high-density fluids, in short, HDFs, which is how I will address these fluids during this talk. And these HDFs are essentially the only direct metasomatic agents which we can use to trace the different processes in the Earth's mantle. These high-density fluids, HDFs, show four different compositional end members, which we can see in this general diagram. We have the saline end member group, which is rich in water and carbonate, together with potassium, sodium, and chlorine. We have the high magnesium group, which we can see here in blue, which includes magnesium, calcium, iron, carbonatite, and of course water and carbonate. And we have the silicic end member group, rich in silica and alumina, which forms an array with the low magnesium carbonatite group, which is also rich in carbonate and carbonatite and silicic end member. We can see that the different end members have been found in various worldwide locations, showing that the processes that form diamonds are alike in different places worldwide. And the origin of these fluids have not yet been established, but they have been connected to geological processes. The saline HDFs have been connected to an origin of subduction, originating from the subducting slab, and upon interaction, the two main lithologies in the Earth's mantle, peridotite and eclogite, they evolve into the different HDF end members. An interaction with peridotite can lead to the evolution of high magnesium carbonated HDF, while interacting with eclogite can lead to the evolve into silicic and low magnesium carbonated HDFs. Using the diamonds, we can also learn about their mantle resonance time. A single nitrogen atom, which replaces a single carbon atom in the diamond, is called a C center. And over time, it migrates through the diamond lattice to form a pair of nitrogen atoms called A centers. And these pairs of nitrogen atoms, over time, migrate through the diamond lattice to form a formation of 4 nitrogen atoms plus a vacancy. This is called B centers. And this kinetic process depends on 2 main parameters. We have the time parameter and the temperature parameter. The migration from one nitrogen atom to a pair of nitrogen atom happens in the time scale of millions of years and depends on usually low temperatures. While if we have higher temperatures, it can affect the migration from C centers to A centers, and from A centers to B centers, that is a time scale of billions of years. So in order to get the full geochemical fingerprint of these HDFs, I use different analytical techniques. I use spectroscopy techniques, including FTIR to get the bulk composition of the HDFs, Raman in order to recognize mineral inclusions. I use different electron microscopy techniques, including EPMA, FIB, and TEM, using EDS to get the chemical composition. And I used ultra-clean laser ablation in water technique in order to extract these HDFs from the diamond, using ICP-MS to measure trace elements, and TIMS in order to measure the radiogenic isotope composition. So my research is focused in an area of a mine called Voorspoed in South Africa, which is part of the Kapperval Craton. It is part of the Kroonstad cluster, a kimberlite or lamperite that erupted 131 million years ago. And previous studies have studied diamonds from this mine, from this location, showing monocrystalline diamonds with mineral inclusions. These mineral inclusions gave us information about high nitrogen aggregation, together with high temperatures, and a unique feature of clinopyroxene and orthopyroxene exsolutions in diamond inclusions that show a cooling of 200 degrees. Another unique feature is that these HDFs have been found in some of these diamonds, but in monocrystalline diamonds, 2 gem quality diamonds showed one saline composition and another one with a low magnesium carbonatic silicic composition. So I will divide my talk into 2 parts. The first part will discuss the upper parts of the mantle, the lithospheric diamonds, and I will continue on to the deeper parts of the mantle, and in the second part discuss the sub-lithospheric diamonds in the Voorspoed. So starting with the lithospheric diamonds, this part is composed of 14 fibrous diamonds. And in this first image, you can see that most of the diamonds show a clear center with this opaque microinclusion look only around the clear center. And if we zoom in, we can see one of these diamonds, for example. These diamonds are called coated diamonds since they are composed of a clear section and an opaque area that surrounds it. We call the clear center a core and the opaque center the coat. And using photoluminescence imaging, we can see the growth patterns of these diamonds. And the clear core part, we can see the monocrystalline growth patterns, while the boundary between them shows that the coat part is a fibrous growth. This may reflect 2 separate diamond formation events. Well, if we can define between their different nitrogen aggregation and their ages, we can see that the core can be one earlier growth episode followed by the growth of the coat surrounding it. So starting with the HDF composition of these diamonds, we can see in the ternary diagram that we get 3 separate fluid compositions from these diamonds. 8 of the diamonds present with a saline composition, which fit very well with the worldwide array. 5 of the diamonds show a silicic composition that fit well with the silicic low magnesium carbonatic array. And one of the diamonds, which you can see here in blue, is a high magnesium carbonatic HDF, but it looks like it's falling into the saline array due to its high potassium. but essentially it has no chlorine, so we define it as a high magnesium carbonatitic HDF. We can also see the difference between these compositions in the variation diagrams. Here, for example, we can see calcium and potassium versus magnesium, and we can see the different chemical compositions. We have the saline HDF group in green, the silicic HDF group in red, and the one high magnesium carbonatitic HDF. We can also see these differences using trace element compositions. You can see here the different patterns of all three compositions normalized to primitive mantle. And in gray behind each one of these patterns, we can see the trace elements of the Voorspoed lamporites. I'm not going to address this during this talk, but we can see that there are differences between the different HDF end members. We see that the saline group shows a pattern that is related to smaller melt fractions, while the majority of the silicic group has a flatter pattern, and the high magnesium carbonatitic HDF group shows an intermediate pattern. Looking at these trace element compositions through the variations of lanthanum over niobium, we can see a linear trend between them, mostly. And we can see that the silicic group shows lower ratios and are similar to compositions of alkali basalts, while the saline compositions show higher ratios and may resemble a subducted interaction. We also measured isotope compositions. Here you can see the neodymium ratios versus strontium ratios. While in this case, we can see that the composition of all three HDFs are pretty much at the same compositions. The isotope compositions are less radiogenic compared to the mantle array, but do show similar compositions to the lamporites from South Africa, and more specifically, the lamporites from Voorspoed and Lace, which is the neighboring mine. And this may imply a origin which is related to lithospheric composition and not to a origin of a convecting mantle. We were also able to measure isotope, lead isotope ratios. We can see with the lead isotope of 208 over 204 that the HDF compositions fit nicely with the mantle array, which you can see here in blue, while the 207 over 204 lead isotope compositions show higher values, and this may imply an origin which is more related to subduction. We also look at the nitrogen aggregation of these different groups, which we can see in the FTIR absorbance. Here we have a FTIR spectra of these different groups, and using that we can define the different parameters of the diamond. We can see an absorption due to the diamond and the nitrogen aggregation in the lattice. In order to see the ratios of the different components of the A and B component to get the different nitrogen aggregation of the diamond, we use a clear spectra of A centers, which you can see here in blue, and a clear spectra of the B center component, which you can see here in red, and we subtract the A center and B center from the spectra that we measure in order to define the amount of A centers and B centers in the diamond. So in the saline group, we can see that it looks like the A center shows a good fit, but upon subtracting, we can see that the residue fits nicely also with a B center component. And the silicic carbonatitic diamond, here we can see already in first sight that the A component does not fit very well, and upon subtracting, we get a much clearer B component, showing that both diamond groups have a different aggregation of A and B components. We also see absorbance due to the HDFs. We can see an absorbance due to water, carbonate, and the different mineral daughter phases in the HDFs. So if we take all this information about the HDF composition together with the nitrogen aggregation, we look at the total nitrogen concentration over the amount of aggregation, we can see a definition into three compositional groups. We have lower aggregation of the high magnesium carbonatitic HDF, we have a group of a saline HDF composition, and we have another group of the silicic HDF together with the saline cores, all sitting around the same isotherms. But in order to define either the time or the temperature, we need a constraint on the time or the temperature. In the case of the fibrous diamonds from Voorspoed, I did not have a constraint on the time or the temperature. So in this diagram, we had to use different parameters of times and temperatures to see their history. To understand it better, we translate this diagram into these two changing parameters of time versus temperature, while each one of these lines represents one of the diamonds. So for instance, if we take a representing time of 1 billion years, and we see where it intersects with, for example, the saline group, we get a certain range of temperatures of their formation, while if we take a younger age of about 1 million years, we can see where it intersects with the saline code group and getting a different range of temperatures. But we wanted to get a better constraint to understand these formation events under Voorspoed's lithosphere. So we gathered all the information from previous studies on different diamonds. And at a first look, it sort of looks like a big mess. There's chaos. A lot of diamonds have formed with a lot of different temperatures and different aggregations. But I will try to break it down and show you that it actually divides into different formation groups. We have one group with a very high aggregation, 100% B centers. This may be due to high temperatures, but that's not always enough to explain the high aggregation, and it may imply a deeper origin. We have another group of diamonds around a certain isotherm, including monocrystalline diamonds with the mineral inclusions. We have a third group, including monocrystalline diamonds together with the silicic HDFs and the saline cores. A fourth group, which is the saline coats, and a fifth group, including the high magnesium carbonatitic diamond and a few monocrystalline diamonds. So if we try to constrain the time temperature history of these different diamond formations, we look at the constraints that we have on the scale of the time and temperature. And since we know that we have mineral inclusions showing a cooling of 200 degrees, we can take the original geotherm, which you can see here in orange, and shift it 200 degrees, which for a new geotherm, which you can see here in purple. We know the Kappa-Val cooling rate, which is 100 degrees per billion years for a 200 degree cooling, and we can calculate that we had a heating event 2 to 3 billion years ago. And we have the Bushveld event, which erupted 2 billion years ago, and the Venstrop lip event, which erupted 2.7 billion years ago. And this heating event may have induced the formation of these diamonds, and we can get different multiple diamond formation events during the cooling of the lithosphere. So if we look at the cooled geotherm and see where it intersects each one of these different diamond formation groups, we can get the information on their time and temperature conditions of their formation events. So to sum up the Voorspoed diamond time temperature history, we can see that we have cluster 1. It has high temperatures, no time constraint, and maybe from a deeper origin. We have cluster 2, which is related to a 2 to 3 billion year ago heating event, showing monocrystalline diamonds and some silicic cores. We have cluster 3, 730 to 330 million years ago, including monocrystalline diamonds, saline cores, and silicic coats. We have group number 4, 220 to 160 million years ago, including the saline coats. And we have cluster 5, which is 160 million years ago, including the high magnesium carbonatitic HDF and the monocrystalline diamonds. And this may have been related to the lamproite eruption, which happened shortly after at 131 million years ago. And we can see two interesting conclusions from this time temperature history. One is that fibrous and non-fibrous monocrystalline diamonds form at the same events. And an independent study, non-related to us, of isotopes of mineral inclusions also confirm this different grouping. But since we are people of little faith, we went and measured our own isotope compositions, and we can see that from the saline coats, we get, looking at the strontium isotope ratios versus the rubidium strontium isotope ratios, the saline coats form a straight line. The meaning of this straight line can be either an absolute age or a mixing line. So to check the mixing, we look at the strontium ratios over 1 over strontium, and we can see that there's no straight line between them, meaning no mixing. And we can interpret the straight line as an absolute age of 780 million years with a large error, which is 220 million years, but it is still more accurate than the timing due to the nitrogen aggregation. So I spent 20 minutes convincing you that we have the time temperature history down according to the nitrogen aggregation. But here we can see that the saline coats that provide this age of 780 million years does not collide with its age according to its nitrogen aggregation, but actually fits the earlier metasomatic event, which includes a completely different HDF composition and an earlier event. So how does this fit with our history? And in order to understand that, we go back a little bit to look at the regional events, the geological events at Africa. Here you can see a map of Africa. During the Neoproterozoic, we had the Pan-African orogeny at 900 to 550 million years ago, which did not directly affect the Capoval Craton here at the southern part of Africa, but had enough impact, geological impact, to induce different geological processes. And this overlaps with the timing of the metasomatic event creating the saline cores and the silicic carbonatic diamonds. And we also have a younger event at 180 million years ago of the Karoo flood basalt volcanism, which did directly affect the Capoval, and does overlap with the timing of the saline diamond coats. So in order to understand how these fluids evolved, we're going to zoom into the lithosphere of Voorspoed at this time of 780 million years ago. We know that at this time we have the two main lithologies that compose the mantle. We have peridotite and eclogite. And as I showed before, we already have pre-existing diamonds that grew during earlier events. So during the Neoproterozoic, we have a subduction-related saline fluids that infiltrate these two different lithologies under the Kronstadt lithosphere. They react differently with both the lithologies. While with the eclogite, they get to a full interaction and they grow the silicic coats and some fully fibrous diamonds. While in the peridotite, they do not reach a full interaction. The diamonds grow slower into monocrystalline diamonds, which are essentially the saline cores. And we get fluid stored as metasomes and leftover fluid in the peridotite. A later thermal event, maybe related to the Karoo volcanism, reheats these leftover fluids, and we get another later metasomatic event, growing these salites HDF coats around the cores. So if we look at all these different events under Voorspoed's lithosphere, we can see that the HDF's geochemical fingerprint preserve different mantle processes and allows us to trace them despite their complex history. From here, I will move on to the second part of the talk, and I will talk about the deeper parts of the mantle, the subcontinental, the lithospheric diamonds. And as I was going through my samples, I saw these two interesting diamonds with this large cloud inclusion in the center. And they resemble the rest of the other diamonds that I see, thinking that they have the regular microinclusion HDF end members. And taking it first to the FTIR, I can see that the first results show interesting results. I can see the regular absorption due to diamond, and we get a absorption due to carbonate with a interesting shoulder to it. And we get no absorption due to nitrogen, which is our first hint that maybe this diamond has a deep origin, since deep diamonds have no nitrogen aggregation, called type 2. And we also see a unique feature of absorption of CO2 absorption-related peaks, which are very rare in diamonds. So taking it to the EPMA, I went to see the different HDF chemical composition, and I could see that, to my surprise, there are any composition that are related to the regular HDF members, but what we did find are inclusions with a composition which is only nickel and iron with very high nickel numbers. And taking it to the TEM, we went to see where the carbonate and the CO2 are that we saw in the FTIR. How does this fit together with this nickel and iron? And here you can see an image of these microinclusions at the TEM. And chemical analysis showed that these microinclusions are in fact gaspite, which is nickel iron carbonate with a nickel number, which is nickel over nickel plus iron, of 89, with the composition of nickel 0.85, iron 0.15, carbon 1.7, which is a little over, but this may be due to the diamond matrix, and oxygen 3. We also saw a very interesting feature of another another inclusion assemblage, these nano-inclusions sitting adjacent to these micro-inclusions, and a void, which occupies about 20% of these micro-inclusions, and may have been where the CO2 that we saw in the FGIR was stored, and it evaporated during the excavation of the TEM foil. Just to make sure that we actually see gaspite, which is a rare form that has not been found in the mantle before, we also found diffraction patterns, and we were able to get 3 different diffraction patterns and define their cell parameters, showing that they're a single crystal with a rhombohedral symmetry and are indeed gaspite nickel iron carbonate. Going back to these nano-inclusions that we saw, here you can see an image from the TEM showing that these octahedral nano-inclusions, which are 20 to 80 nanometers in size, are filled with nitrogen. And another interesting feature that we saw, that in the corner, the apex of each one of these nitrogen nano-inclusions was a teeny tiny little bright spot, which essentially was made out of the composition of nickel, which surprised us. And if we take a closer look at these nano-inclusions, here we can see 3 of these nano-inclusions and a very tiny little bright spot in their apex, and we were able to get a better analysis of these compositions, showing that they are very small, they're less than 5 nanometers. They are composed of a nickel number, which is nickel over nickel plus iron, of 85. So we have 2 nickel-rich phases in this diamond. We have an oxidized form with a nickel number of 89, and we have a reduced form of nickel metal in the apex with a nickel number of 85. An oxidized form and a reduced form should not exist in the same diamond. They need different conditions in order to evolve, but they do share a similar nickel number, which implies a shared source. So for this, we needed a nickel-rich source in the mantle to explain how we could find nickel with such a high nickel number. Around the inclusion cloud, we found mineral inclusions. These mineral inclusions were 1 to 20 microns in size. Some of them we were able to recognize using Raman spectroscopy. We recognized them as deep upper mantle assemblage minerals. We saw ulvospinel, new aluminum phase, and for example, here we see an inclusion with 2 phases, a sodium aluminum pyroxene together with olivine. And we were also able to use some of these mineral inclusion spectra in order to gain a constraint on their pressure. So we're using the shift of the Raman band to see that we have pressure estimations of where these diamonds formed. So using all the different phases and their pressure estimations, we were able to gather a range between 9 and 16 GPa, which is very high pressures, and which is translated in the mantle to 180 to 470 kilometers, very deep in the mantle. Here in this area, we have 2 nickel-rich phases, an oxidized form and a reduced form with a very high nickel number. And we see that at these depths, nickel and iron alloy is predicted to precipitate according to thermodynamic calculations. So looking at a diagram of oxygen fugacity versus the pressure relative to delta iron wurtzite, we can see in red the line that describes the mantle oxidation state, and it becomes more reduced with depth at around 250 kilometers, where alloy phases or metal phases start to stabilize. We can see a change in the oxygen fugacity, and under 250 kilometers, this is where we have stable metal phases. According to the reaction of nickel and olivine, which becomes less stable with depth in the reducing conditions, it starts to precipitate as a metal. The reaction of nickel metal plus SiO2 plus O2 around 250 kilometers, and it starts to precipitate an alloy with a nickel number of 60, and with depth and more reducing conditions, the alloy becomes richer in iron, and the nickel number becomes lesser. But in our case, we have a nickel number of 90, or almost 90, which is higher than the anticipated nickel number, which is 60, this reaction called a nickel precipitation curve. And we also have the reduced phase and the oxidized phase coexisting in the same diamond, meaning we have to find a different explanation where this nickel number, such a high nickel number, can exist. And we suggest that a carbonate influx coming from a subducted slab infiltrates the mantle at this depth, changing the different oxidation conditions, becoming more oxidized, and allowing the nickel to become more stable. Iron, which is less stable under these conditions, recedes back to the silicate minerals, and the alloy is enriched in nickel to reach a number of 89. We could describe this using the reaction of nickel metal plus carbonatitic melt plus pyroxene leads to the formation of diamond plus nickel carbonate and olivine. Well, essentially, the diamond captures this reaction and preserves it to show a snapshot of this metasomatic reaction, because interestingly enough, we can see each one of these different reactants and other part of the reaction together and under the same diamond. So if we take a schematic look of a mantle cross-section, here we can see the subducting slab infiltrating the deeper parts of the upper mantle, a carbonate fluid or carbonatitic fluid infiltrating the mantle, creating these more oxidized zones, changing the oxidation state in the mantle, and allowing the growth of these diamonds and the nickel carbonate. If we're lucky enough, a plume may sample these oxidized zone and result in higher nickel numbers in the olivine, as we see in Hawaii, Baffin Islands, and other places around the world. So to sum up the second part of this talk, we can see coexisting nickel carbonate and nickel metal inclusions confirming the presence of nickel-rich alloy in the upper mantle. We can also see that carbonate metasomatism plays a role in increasing the oxidation state of the sub-lithospheric mantle, and that these diamonds provide a snapshot of a metasomatic reaction in the making. To sum up these past 5 years, Voorspoed HDFs highlight mantle processes in which metasomatic agents formed and evolved, and their connection to large-scale regional magmatic events that shape the Kapoval lithosphere, and that both lithospheric and sub-lithospheric diamonds from Voorspoed demonstrate the evolution of carbonate and water-rich mantle melts and their role in diamond formation and their global circulation of volatiles through Earth's history. So I would like to show my deep appreciation for all the people that made this happen, the academic and the administrative staff, including Keren and Maggie and Mali and Yossi and Helena, and everybody that contributed, my fellow research students, specifically Oded Elazar and Amit Meltzer, who were my support group during the first part of the PhD, Yael Ebert and Ophir Tirosh, who were my support group during the second part of the PhD, my committee, Ofra Klein Ben David and Yaron Katzir, my collaborators, Oliver Zoner, Tim Holland, Sergei Remnik, Yana Kornif, and Gareth Davis that helped with the different measurements and interpretation. And of course, my supervisors, Oded and Yaakov, that put up with me during this time. And a special thank you to my family that did not disown me during this PhD. I'll end with a video of a very nice diamond with a perfect cloud inclusion right in the center that Yaakov Weiss never let me cut, and is waiting for the next student. Thank you very much for listening.
That's 4 minutes shorter than what happened yesterday.
Ran through a little bit, so.
So we have lots of time, so if you're interested in asking anything, words that you didn't understand, or...
I apologize, I ran through too fast.
Yeah. Okay.
So Yael, you brought very nice evidence for these metasomatic processes that are related to subduction around the Pan-African events. Now, if you take the whole 780 million years, okay, plus or minus 200, but this is the Pan-African event. So if you look on the entire craton, are there any other places that you see the same kind of evidence? And if there are, can you somehow connect them and try to identify where all the subductions are?
Well, Voorspoed is a very small mine, and it hasn't been researched a lot, but around the South Africa, the Kapoval Craton, there are a lot of different diamond-forming mines, and we can use the different mines and we compare them. They show a lot of A lot of them show a saline fluid around the same time, and we're trying to create a connection which is larger, talking about the larger history of the Cap of Val and connecting all these stories from these different mines to see if there's we can connect it to much bigger regional tectonic events, implying either subduction or these metasomatic events that are connected to each other in time. And well, I would say Voorspoed is a little bit different, but we have seen that these different mines do connect to the Karoo flood basalt event. We see all different saline events that are connected to the Karoo flood basalts from different mines, and we see that here too.
And do they have the same age constraint that you have? Because you have a very good age constraint.
I'm the first time that we were able to find a strontium rubidium age constraint. Right. This is the first study that was able to do that. But if we look at the larger strontium, neodymium strontium isotope composition, I didn't point it out during the talk. There we go. I didn't point out during the talk, but here you can see that a few previous studies that have been done on isotope composition in diamonds. In gray, we can see some of these diamonds from Canada, and these are diamonds from South Africa and Russia, and they show a pretty similar isotope composition. So, right, so we're still figuring that out, and we're trying to see if they relate to either subduction or larger regional tectonic events.
Okay. More questions? I would add.
Great talk. I was wondering if you can kind of break it down for us. How do you get from a metasomatic event or circulation to tectonic activity? Like what exactly is
the connection?
Sequence, yeah.
Yeah. So. As I mentioned during the talk, the lithosphere is a pretty complex place. The lithosphere, it goes through these depletion events and then enrichment events, which come one after the other, right? They erase the previous events. Each one of these events forms diamonds, or can form diamonds. If we're lucky enough that they form the diamonds, the fluids that are trapped in the diamonds are directly connected to the metasomatic events, so these enrichment events. And by connecting their timing, we can see how, if we have a large magmatic eruption, how does this affect the lithospheric part? So if we have heating due to a large magmatic eruption, like I mentioned, the Bushveld event or the Venstrup event, this has an impact not only on the upper parts of where we can see the surface, but also on the bottom parts, either if it's heating or if it's subduction. So we take these relics of these fluids, which are the direct metasomatic events, and we usually don't see. They react with the mantle, and then something else happens, and they're erased. But as the diamonds form and they capture these, they record, I would say, these formation events, we can see how they relate to the tectonic events. And as I showed in the talk, we can see that there usually is a connection. If there is a large tectonic event or a geological event, it also affects the lithosphere, and we can see how these diamond growth events are essentially connected. Did I answer the question?
Yes.
Yeah.
I have a question, a comment about the nickel. I think it's very interesting because also the alkali basalts are enriched in nickel. Now the alkali basalts they don't come from these deep depths, right? They come maybe from the subcontinental lithosphere, the depths of 60 kilometers, 80 kilometers, maybe 100. So do you think that this process that you are suggesting here for the enrichment of nickel could be also the source for the enrichment of nickel in basalts in shallow levels of the lithosphere?
It's a good question. I would say that there's about 3,000 ppm nickel in olivines and peridotite, and changing the oxidation zones, or the oxidation conditions in the mantle allows the nickel to become more enriched, essentially. So I would say it depends on these areas. If we see that these carbonate influxes do change or do influence the oxidation state of the mantle, it is not as simple, I would say, or clean as it is seen through thermodynamic calculations or experiments. So these changes may exist in the oxidation state. And depending on the conditions of where these alkali basalts form, they may have a change in the oxidation conditions, which allows the enrichment of nickel. Or the source of the nickel, right? The peridotite, exactly. So it may have affected it in the deeper parts, and we have these oxidized zones changing the nickel ratios in the olivine, and then or in the peridotite, and these migrate through the lithosphere and be caught by different basalts or different processes that sample them and bring them to Earth.
Okay. Can you go to the trace elements pattern?
Do I have to?
Spider diagram.
Okay.
Yes.
What I'd like to comment on Moti's point.
Yes.
You can see that the concentrations of the incompatible elements here are around a few hundreds, which means that we take all the incompatible elements from the rock and put it into the melt. Yeah? So we talk about melts that are less than 1% melting. So every little heating of the lithosphere or the asthenosphere cause this melt to become mobile, or cause these things that maybe crystallize to go back into melt, and they can move. Yeah, I think that the alkali basalt source region experience enrichments of such melts. You do not have to move the melting of the actual alkali basalt. You can bring things from deep in series of steps and reach the source and then melt it.
But here it's also about the nickel. This is a very interesting point. Right?
Yeah, but nickel is not in all alkali basalts. Some alkali basalts are enriched in nickel. Okay.
Also,
on behalf of the audience, I'd like to ask.
I just want to add to what you just said, that if we look at this rising plume, it may raise it to the surface, but it may also raise it to shallower parts. And then it sits here with the higher nickel number, and it is sampled by the different alkali basalts. So it's not necessarily brought from here to the surface, but they do exist in the mantle. And if they are caught by this rising plume, they may move up a little bit, not necessarily to the surface.
Okay. Last, I have a question.
Yes.
On behalf of, I think at least half of the audience here. What's the hell is metasomatism?
Metasomatism, yafe. I was wondering if I should explain that or not, or if it's common knowledge. But metasomatism is the process where fluids interact with a lithology or a rock and create changes in this rock due to its infiltration. So if a carbonatitic melt goes through the rock and changes it, this is metasomatism.
Before alkalinity, metasomatism was the most secret word in geology.
Okay.
Okay.
So, thank you very much, Yael.
זה פה מול כולם, אני לא חשבתי שזה יהיה מול כולם.
היא יותר פוחדת מה-60 שניות האלה מה שמעת מההרצאה עצמה, אז נראה אותה.
נכון. גו. יהלומים נוצרים בחלקים עמוקים של הליטוספירה, ומאפשרים לנו לדגום את החלקים העמוקים האלה של הליטוספירה ולחקור אותם. אני חקרתי יהלומים מהמכרה בוורספוט, בקפבל בדרום אפריקה. היהלומים האלה מראים קשר גיאוכימי בין אירועים טקטוניים לבין היווצרות של יהלומים. בנוסף חקרתי גם יהלומים מהחלקים העמוקים יותר של הליטוספירה, שני יהלומים שמראים בפעם הראשונה ניקל קרבונט ביחד עם ניקל מתכתי. הריאקציה הזאת היא דוגמה לאיזושהי תמונה שנוצרת, ריאקציה שנוצרת במעטפת, שנלכד על ידי היהלום, ומראה לנו איך אינטראקציה של נוזל שהוא יותר מחומצן, מגיב עם אזור יותר מחוזר, משנה את התנאים שלו, ומאפשר לנו לראות איך דברים אחרים במעטפת גדלים, למרות שהיינו מצפים אחרת.
57 שניות.
בול.